Okay, so I believe the screen is visible now, and very good afternoon to everyone present today in this event. So if you look at the title of this talk says words too are known by their friends. So there is a saying that you are known by your friends, people are known by their friends. So whatever your behavior is, whatever our behavior is, and all that, many a times those things get influenced by whom we have in our surroundings, right? Whom we interact a lot with, and so on. So the same thing as people are saying now happens for the words also. Okay, the title is actually a bit long, so we'll slowly, when we go through the presentation, we'll possibly be able to understand what we mean by this. The words too are known by their friends. Introduction to word representations. So among the audience, can anybody guess what is the domain or what is the broad topic from which this discussion is coming in? So actually, it is coming from NLP, or natural language processing. So if you look at last year or last couple of years or last few years, there are lots of learnings that we have received depending on the situations in which we are in, depending on how our surroundings have been very fluid, and things are changing a lot. There are quite a few learnings that we all have got, irrespective of our occupation, our background, our surroundings, and so on. One of those things is that communication is very important, right? It is very much essential to communicate with our friends, our peers, our family members, and often with business also. And if you look at all these communications that is happening now, irrespective of the channel or mode of communication, for example, is it a video call, is it an audio chat, is it some chat over some messaging platform, even again for this audio communication, video communication, chat based communication, there are many platforms. Irrespective of whatever we use, the main mode of communication is natural language, right? And natural language has been a mode of communication since long. It helps us in easy expression, and also through this communication we are often able to take important notes, pass on our judgments, our sentiments, our opinions, and so on. And hence, communication in natural language processing, communication in natural language has been very important since long. There is another thing that we see has changed a lot or is changing a lot in recent times. That is, there are many tasks and services and applications which are moving to the digital space, right? So if you look at our news reading habit, right, we consume a lot of information from different news websites or news magazines which have their presence in the online world. If you look at the legal documents, the legal judgments, the Supreme Court rulings, different High Court rulings also in different languages, now those are being stored in digitized repositories. A lot of our purchase decisions have also moved online, right? We tend to buy many things online now, and at the same time, before purchasing and after purchasing, an important factor that comes into picture is the reviews. Even if you go to any hospital nowadays, what we say is that the patient health records that is also going into the digital space. When a doctor, when a medical doctor examines somebody, looks at the report, and then gets his or her own judgment, even that transcript is going to the digital space. And all these, or at least most of these, are there in natural language. Now, in these changing times, when we are slowly getting accustomed to the online world, when we are slowly getting accustomed in the digital space, it is very much important that all these kinds of natural language text which is getting generated and many times getting stored in such platforms, that needs to be analyzed so that important and intelligent decisions can be taken based on this content. To re-emphasize on the last part of what I just said just now, important and intelligent decision makings which can help people, okay, and these decisions are taken on the basis of the different natural language text which is available on the web. To re-emphasize on this point, let us have a look at few simple examples. Okay, so as I said, and as we all know, that a lot of legal documents now are appearing online. So those are the high court rulings, the different judgments. Now suppose there is a legal expert who wants to find out similar judgments. Okay, so he has a case and then he is trying to see what could be the relevant prior cases for this. What are the scenarios where this kind of judgments were given? Searching this kind of information is not very easy. Coming to e-commerce, many times before buying a product online or even before purchasing it from offline store, many times we go online and we search for the reviews of that product in those e-commerce sites. We try to find how people felt about the product. Even if you look at the sellers, the brands and so on, even they look at this information and try to find out what is people's overall sentiment, what are the different things that they are liking, what are the things that they are not liking, and all that. Even understanding this information from a huge repository of natural language text is not very easy. Then if you look at social media posts, so many of us are now getting glued to social media due to various reasons. Sometimes people join or people spend time in social media to pass their time. Many times it also becomes handy for different reasons. So we have seen that during the lockdown period, there are many small entrepreneurs and there are many first-time business people. They started selling off their products and connecting to people through the social media. And they were very much receptive to the different comments that they received for their products on the social media. During different disasters, now what we are seeing is that people are becoming very active in social media and they're posting the different requirements at different places in social media. For example, uh, during the Nepal earthquake uh, or even during the last year's Amphan, there are a lot of posts in social media where people said, we need tent at this location. This place is completely waterlogged or something has broken here. Okay, and there are a few people who are trapped inside. So this kind of information where it is very difficult to reach the site due to infrastructure damage and so on, this kind of information actually give us the ground reality, which otherwise would have been very difficult to obtain. And accordingly, the rescue and relief operations, they can be handled or taken care of. So again, a lot of social media posts which are coming in every minute or every second, from that filtering out this kind of useful information is again a very, very important and a very, very crucial thing. If you look at news articles, we are going through news article and then we want to show who are the other publishers who are covering the same news article. Sometimes to see what they are saying, what are the differing opinions, sometimes to get more elaborate opinions, to get more details, we generally try to find out articles which are similar. And if you look at all these examples, the main content is in natural language form. So the bottom line or the take-home message that we want to get from this slide or the discussion till now is that it is very, very important to be able to automatically process and understand natural language text so that we can make many intelligent and interesting decisions, which can also be very helpful. So with this premise, let me move on to the next part. So here essentially what I have given is some applications which are algorithm driven, and the applications vary, right? So suppose somebody wants to take up a task and design an algorithm. So this will be a typical block diagram, right? So at the center you have the algorithm, right? And this algorithm will take as input some textual content which I have written here as documents, and finally it will generate some output. It can be a classification, for example, say for an example, how did the person felt about the product? Was he happy, unhappy? It can be something like, does the social media post talk about a disaster, or does the social media post talk about need of resource at a particular region or not, and various other kinds of things. It can also be something like, you have a collection of documents and you have a query document, and you try to find out all the documents which are close to that query. So in that case, the output will not be a singleton but a set. So what happens is, whenever we try to use an algorithm for a task, one thing is, we can curate our input representation according to the task, right? We try to guess what are the useful information at hand that can help us in making that decision, and accordingly the input is prepared. On the other hand, one can think of a situation where all the inputs we have with us beforehand, and we already decide on their representation, okay? And then that same input representation can cater to different needs for different tasks. So for example, you have a collection of documents, you decide on some representation scheme of the documents. So as long as you are with your document collection, the representations are not going to change. Now with that same document collection, you can try to perform different tasks, right? It can be finding the documents in the same cluster of this document, finding whether the sentiment expressed in this document was positive or negative, or it can be something like find the summary of this document. So the algorithms and the tasks are different, but we pre-decide on the representation of the input, but the algorithm and the outputs are task specific. So if we want to make use of this, the below block diagram, the very essential question remains, how do we represent the documents? So in order to answer that question, the thing that we try to zero in is that the basic unit in a document is word, right? So the meaning expressed in a document depends on what are the words that are chosen. So basic unit of representation in a document is a word. The thing is, can we make use of these words or terms to represent the document? So there are many different ways in which people have traditionally attempted to represent the documents like this. One thing, one of the approaches would be, you look at all the different words that are present in a document, and you represent the document using a set or using a collection of those words which are present in it. For example, suppose you have read a book and you are not able to recall the name, but you know that, okay, in the book there was mention of a boy called Swami, and there were some of his friends who were Rajam Mani, and the setting of the story was a village in Tamil Nadu. So these words that you remember essentially give you some information about the document. So you can approximately try to represent the document by these words only. So essentially, you are representing the document by using a bag of words or a collection of words approach. Now, can anybody guess what is the book that I am referring to here, which has these terms? Swami Rajam Mani Tamil Nadu.
Malgudi Days.
Malgudi Days, yes. Now, it's a book of many pages, but we have identified only a few words that possibly would represent and would possibly distinguish it from many other books, right? On the other hand, if the document is not very large, we can think of representing it by using a set of all the terms that are appearing in the document. So that is one extreme of representing the document. Now, one thing here, when we say document, it may not be we are not referring to a book or a large newspaper article or a Wikipedia article. Sometimes a
कह रही
newspaper,
हूँ
sometimes
एक
a
वेबिनार
newspaper,
था ना इस पे
yes,
मशीन लर्निंग रिसेंट ट्रेंड
I request
एसोसिएशन
all the audience to please keep yourself muted.
हाँ
Vijay Kumari.
तो वो मैंने तेरे पास भेजा था तो मैंने तो
okay. So let me go on. Sometimes the headline of a news article, even that can be a document. Okay. Sometimes a social media post, which is, say, for example, 140 or 280 characters, even that can be a document. So an input text segment, that I'm referring to as a document here. Now, if we use the set-based representation as I just spoke about, as we know, in a set, we generally do not repeat the items, right? Each item is counted only once. But then people felt in a single document, for example, suppose a Wikipedia article that is talking about diabetes and its cure or treatment, right? It will use the word diabetes a lot many times. It may use the term treatment many times, right? So all these words which appear a large number of times in a document, so somehow that represents the characteristic of the document. So each term has its own importance. So instead of representing the document as a set only, try to represent it as some kind of vector where each field corresponds to a term. Okay, and then in that field you store something, maybe a number, which represents the weight of the term, and many times this weight can correlate with the number of times the term appears in the document. And the first one that I mentioned using the set approach is often called a Boolean representation of the document, and the second one way of achieving this is term frequency, inverse token frequency, and so on. Now, this traditional way of storing the document representations, it went on for many years, and there were many applications which were developed based on these kinds of representation. Again, as we see, this representation is task agnostic. So once we have the vector representation of the input text, many different applications, many different algorithms can run on that. But nowadays, people are, I mean, when I say nowadays, in the last 7 or 8 years, people have, identified this these drawbacks were known before. Now there has been a line of research where people are trying to have some alternate ways of representing documents, where they say that you have some kind of understanding about the representation of the words and let the document representation be computed from those word representations. So that is going to be the focus of today's talk. Word, how do we represent them? And then we will see how that representation can be used to represent documents, and using that representation, how we can solve different tasks for document or language processing. So to give an example, so suppose we have one document which talks about Farm Bill 2020. So I believe I don't need to explain anything more than these three terms. It gives you some kind of idea about what can be contained in this document. Now suppose you see another document and this says that Farm Bill 2020 explained. What is it? Now do you think A2 is related to A1? I guess it is related. Now suppose the third one is software verification primer. So there is a document with headline or with title software verification primer. So we can say that A1 is not related to A3. Now before we go to the A4, let us look at A1 and A2 again. Now I said that A1 and A2 are related, and I would think that many of you or all of you would agree that A1 and A2 are indeed related. Now what makes you think that A1 and A2 are related? Can anybody cite any reason? Okay, so let me give my reasoning here. So my reasoning here would be, see, Farm Bill 2020, all these three terms are present in A2, and it gives a very clear indication that A1 and A2 are related. Next, that same thing didn't happen for A3. Now let us look at an interesting case, A4. It should be why is the Agriculture Act being opposed? Okay. Do you think A1 and A4 are related?
Yes.
Yes. And what could be the reason or justification?
Maybe farming and agriculture, the contents.
Right. So we know, based on our linguistic knowledge, that farm and agriculture, these two things mean the same thing. Bill and act mean the same thing, and we can say A1 and A4 are related. And then if we are following current affairs, we know that yeah, I mean there are many discussions, debates which are going on based on the farm bills, and this title appears to suggest that it's a document which talks about that kind of discussion. Now, one thing to note here, A1 and A4 didn't have any word in common, but there were a few words which were kind of synonymous, or they captured the same semantics. Now, if we look at A5, A1 and A5 are not related, although there is this bill and bill which is matching. So we could give our judgment, very reasonable judgment, depending on our understanding of the language and based on the way we interpret things. On the other hand, if the same thing has to be done, for example, given A1, which of the next four documents are related to A1? If a computer needs to make a judgment regarding that, how will it do it? Do the same thing. On the other hand, suppose we do this, we pass on the right side figure to the computer. So what is there? So for the 5 documents, we have 5 different points. Okay. Suppose these 3 points, they are about A1, A2 and A5, A4. This is A5 and this is A3. So the computer or the system has the representations, vector representations of A1, A2, A3, A4, A5, and given A1, it has to give us what are the other points, and each point represents a document. What are the other documents hence which are close to or which convey the similar kind of meaning or similar kind of content as A1. Or okay, let me rephrase what I just said. So the computer is given all these 5 points, and then it is also given this point as a special mention that okay, it is A1, and give me the other points which are very close to A1, and it can give that very quickly. Now it can give it even if these points are not in 2 dimensions but say 1000 dimensions or 10,000 dimensions, because computer can do that kind of job very fast. So we can do this, we can process this part very easily, computers can process this part very easily. The question is, can we make a connection between these two so that our natural intelligence can somehow be artificially embedded in these kind of representations, so that the computers also can do the similar kind of task with a very high degree of confidence. These are nothing but representations of the documents, or what I'm trying to say is that, is there a way in which we can we can create very crisp and correct, in some sense, okay, good rather, representations of different natural language inputs, so that there can be algorithms which can process that data very quickly, and that can help us in taking or in making intelligent decisions. Okay, so these document representations, as I said earlier, there is a recent trend in which people say, let us get these document representations based on the word representations. So we are talking about representing documents as vectors, but also representing words as vectors. Question is, words as vectors, didn't we already have it? So yes, when we were talking about the vector space model or Boolean representation, TF-IDF representation, we were actually referring to this kind of vector space only. So if we assume that in our dictionary there were three words, hi, hello, and world, one way to think about that vector space would be there are three dimensions, one for hi, one for hello, and one for world. Now, if there is a document hi world, it will be having, this, it will be represented as a vector like this, which may be say 101. Now, if there is a word called hello, it can be represented, if there is a document called hello world, it can be represented as 011. So we are getting the document representations, and the representations for the different words could be 100, 010, 101, right? So traditional vector space model anyways represents the words as one-hot vectors, because all these different numbers, all these different components of the vector correspond to one different dimension, and each dimension corresponds to one word. Okay, so for hi word it is this axis. For the word hello, it is this axis. For the world, it is this axis. So although it is there, we see that words are independent of each other. They're orthogonal. Now we can say that, okay, hi and hello are very related, but if you look at the dot products of these vectors, that is 0. And hello and world, that dot product is 0 again. So irrespective of whether the words capture the same semantic meaning or not, whether they are related or not, every time we have the dot product as 0, indicating the words are independent of each other. At the same time, every pair of words is equidistant from every other pair of words. So if you look at the distance of this point and this point, or this point on this point, so if you have n points or n words, you can compute n choose to many pairs of distances, and you will see that in each and every case the distance is coming out to be the same. So which again indicates that we are not able to capture the semantics of the different words in this kind of representation. Okay, so, and then there are some additional issues like sparsity, vector length, and so on. So if you want to represent our documents, for example, the Malgudi Days novel, or say the Lord of the Rings novel, using such a vector, we have to have a vector space. Okay, we have to have the number of dimensions very large, right? Which can be, say, each word in the dictionary, English dictionary, along with few proper nouns and so on. So it can easily go to, say, lakhs or millions. And processing these large vectors becomes very difficult. At the same time, they will be very sparse vectors. There will be many terms from the dictionary which are not represented in a document. Then people felt that, can we have dense vector representation of words that also keeps the semantics intact? So words which are similar, they can have very similar kind of representations. But two words which are completely different and they are used in different, completely different contexts, so their vectors can be quite different. So the Q, this is actually from Wikipedia. It says words that are used and words that occur in the same contexts, they tend to purport similar meanings. Okay, words that are used together, they are possibly related, and words which appear in similar contexts, which are surrounded by similar type of words, they mean the same thing. generally. Okay, so if we say horse eats grass, cow eats grass, buffalo eats grass. So the words horse, cow, buffalo, they are all getting used or along with the other words eats, grass, and so on. So maybe there is some commonality among those words. Okay? So words that are used and occur in the same context, they tend to have similar meanings. So this is why this is the thing that we want to make use of and get the vector representations. So what is our goal? We want to represent each word using a low dimensional vector. Okay. Now when we say low dimensional, from 1 million dimensions, we are actually thinking of dimensions of size 100 or 200, like that. And word similarity would be represented by the vector similarity. And the key idea of getting these things is that we need to observe the surrounding words of every word. And how do we get these vectors? Who gives us these vectors? Nobody gives. Algorithms will learn it themselves. Okay, so we learn the vectors or these embeddings. So this kind of algorithms are known as representation learning because we are learning representations of the words. They're also called word embeddings because we are embedding the words in some high dimensional space. So below is one embedding that some people got based on their data set. You see that cheetah, jaguar, tiger, they are in the similar space. I mean, in a nearby space. Then pelican, seabird, finch, they again are clustered together. And then flower, leaf, foliage, plant, all these things are again sitting in a close or dense subspace. So this is the kind of thing that we want to get, and we want to do it in an unsupervised way. What we expect is that we'll have some collection of documents, and from that these kind of representations will be learned automatically. So it's not a very new thing or very new thought. So I'll try to give you some representation learning algorithms. I'll walk you through some of them. I'll not go into the complete details because we don't have time for that, but I'll be trying to give you some pointers that you can follow later on if you're interested. The first one was singular value decomposition. Singular value decomposition, as many of you would know, is an algorithm from linear algebra, and it is there since long time. Okay, so what singular value decomposition says that is that if you have a matrix A which is of m cross n dimension, there exists a factorization A equal to u sigma b transpose. Okay, you can break A, you can factorize A into a product like this, and these will be the dimensions for obvious reasons. A should be m cross m, sigma is m cross n, b transpose is m cross n. So this is so that this matrix multiplication is allowed or compatible, and at the same time the product is you get back m cross n, which is the original dimensionality of A. And if you do this singular value decomposition, the things that you can observe, I mean, it comes from again the theory of linear algebra. The columns of U will be orthogonal eigenvectors of A transpose. So if you have A, definitely you can compute A transpose, and then definitely you know how to compute A transpose. And once you have A transpose, again, it's not difficult to observe that it is a square matrix, and it will actually be a positive symmetric definite matrix. It will have its eigenvectors as orthogonal eigenvectors, and those orthogonal eigenvectors will actually sit together in the columns of U. Similarly, the columns of V will be the orthogonal eigenvectors of A transpose A, and the sigma will be a collection of singular values. So given any matrix A, you can decompose it like this. Okay? And yeah, this is some, if your A is like this, U sigma B transpose would be like this. But this is something from linear algebra, and why are we referring to that while talking about words and documents? So if you have a document, right, so you can, from this document, you can create a term document matrix. What does a term document matrix mean? So it's actually a matrix where the rows are the terms and the columns are the documents. You can actually have the transpose of this and call it a document term matrix also. So here I'm calling it as a term document matrix. Rows have terms and columns have the documents. And these numbers denote the weight of the word in this document. So for example, you can assume that the word complexity appears 2 times in D1. D1 has algorithm 3 times, D1 has entropy 1 time, and these 2 terms are not present there, and things like that. Okay. So once you have this term document matrix, it can be your original matrix C or A, as we mentioned in the previous slide. So it is M cross N term document independence matrix, incidence matrix, meaning there are m rows and n columns. So in this example, m terms and n documents. And now you can have a singular value decomposition of this. And if you have C, which is a original SVD, you can do something like truncated SVD by suppressing some of the low singular values in sigma. And if you, how do we suppress? We make them zeros. Okay. So these were the values in sigma, and typically they are ordered in decreasing order. And suppose instead of these 3, we want to set k equal to 1, that is we want to retain only one singular value. So these smaller singular values, we can make them zeros. And since we are doing matrix multiplications, you will see that some rows and columns from these matrices will now be ignored because these things are getting zeros, converted to zeros. And essentially the leftover term, yeah, so if you make this thing as 0, you will see that this has no effect because all these entries in this matrix multiplication would have got multiplied with this. Similarly, all these entries in this matrix multiplication would have got multiplied with this. So this has no meaning now. This has no meaning now after you have set this to 0. So in other words, in U, each row now has k dimensions. In V, each column now has k dimensions. And what is the significance of U and V here? So this C was your term document matrix. So U was M cross N, sigma was N cross M, and V was, sorry, U was M cross M, sigma was M cross N, and V transpose was N cross N, right? So now this M cross M has become M cross 2, the sigma has become 2 cross 2 after we retain these 2, and this has also become 2 cross N. In other words, each term, so you had M rows, right? You had M rows, and these M rows corresponded to these M terms. We had N rows and N columns, and they correspond to the N documents. Now what will happen? In U M cross 2, you will have 2-dimensional representations of the terms complexity, algorithm, entropy, traffic, and network. In V transpose 2 cross N, that is in V N cross 2, you have 2-dimensional representations of the documents, okay, in each of these documents. So that means we have been able to represent the documents from 5 dimensions to 2 dimensions only. We have been able to represent the terms from 5 dimensions to 2 dimensions only. Okay, so documents now can be represented using the, okay, I think this is incorrect. Terms now can be represented using the entries in UK, and we can work with k much less than n dimensions. And terms, the documents can be represented using the entries in VK, and we can work with much lesser number of dimensions. So this is an algorithm which simultaneously gives us the representations of the words, that is the terms, and also the documents. As I said, it's not a very new approach. It was there even in 1990s where people used this. So essentially, you know, these people were from Microsoft Research, and what they did is they took 9 different documents. Some of them came from human-computer interaction, and some of them came from graph theory, and they got the term document matrix. Then they applied SVD. Then they reduced the SVD to 2 dimensions by using truncated SVD of k equal to 2. And whatever representations, the 2-dimensional representations they got for the documents and the terms, that they represented in a plot like this. And what you see here is that terms like time, response, user, computer, they are close by, right? So we are learning very good embeddings for the terms. Similarly, graph, tree, they are together and they are far away from user, time, and so on. Human interface, they are again together. Now, if you look at the document IDs, M1 to M4, they are about graph theory, and C1 to C5 are about human-computer interaction. And what we see is that M3, M4, M2, all these M documents are nearby, and all the C documents are again nearby, but far from the M documents. So this was about SVD. What we did is we took a BBC dataset, which is a collection of news articles, and there that document we fed to SVD algorithms, and for each term we noted the vectors. We used 20-dimensional vectors. That is, we set k equal to 20 for the truncated SVD, and whatever term representations we got, we fed it to a clustering algorithm to get some 10 clusters. And we saw that cluster 0 was giving us mobile, broadband, digital technology, and all these kinds of terms. In cluster 1, we had musical, comedy, film, these kind of words. Cluster 2 had terms like economic, growth, economic, dollar. So what we see is that the groupings of the terms are actually now getting very good. So cluster 9 had Labour, election, Blair, so UK politics at that time. So all these things, this representation was very easily able to get. So similarly, we took academic publications and then we ran SVD, and on top of the SVD results, we had the clustering algorithm. And what we see is that cluster 0 is possibly talking about Bayesian inferencing. Cluster 1 is possibly talking about classification algorithms. And this one is possibly talking about artificial neural network. This one is also about artificial neural network. Cluster 8 is possibly talking about optimization algorithm and so on. So then what people thought is that SVD also, although it is a very powerful algorithm, right? But in real world, that original matrix C or A will become huge. I mean, we talk about documents. If you look at Google possibly now indexes multi-billion documents, right? And there are millions of terms. So billion plus million metrics and then operating on that is a nightmare, and it's very difficult, and sometimes it will not be feasible also. So can we do something else? Then this algorithm came in 2013, which said that if you look at any word in a document and then you look at the surrounding words, okay, define a small context window. So here we are defining a context window of size 5, that is the current word, 2 words next, and 2 words previous. So what we do is, in this algorithm, what it does is, for each term in the collection, it initializes it with a vector. Okay, and then it tries to, it makes sure that the representation of this term can be dictated or can be modified by the representations of these terms. So that's what we mean by words and their friends. One word's representation will be modified by the friends, that is the other words in the context. So if we do that, definitely the representation of this will change. Similarly, if we shift our attention to this word, its representation will be changed by its neighbors, and so on. This goes in an iteration. So what is observed is that after a few iterations, the representations, they do not change. Representations of any given word, that does not change much. So in other words, a convergence can be reached, and that will be the final representations of the words. So this word2vec had 2 different variants. One is skipgram and the other one is continuous back of words. In skipgram, what happens is that given this target word, okay, we want to predict the context words, right? So we want to predict the probability of this. And this prediction, probability prediction, is actually modeled as an optimization function. And a neural network learns to optimize that optimization function. Okay, and in continuous bag of words, the opposite thing happens, where it says that, okay, if I give you this these context words, can you predict what was the central word? Or assume that this is hidden, this is masked. Now, given this W minus 2, W minus 1, W1 and W2, can you predict what would have been the entry at C? So essentially, for each word in the vocabulary, it can give a probability that this is the word sitting here. And we expect that for the correct word, this probability will be very high. So this is the objective function. This is the probability that this algorithm tries to maximize. And this is how mathematically the same thing can be written. In interest of time, I am skipping this part. So essentially, you have a collection of sentences or documents. You go through them one by one. Okay. So firstly, suppose you are at this sentence. This is your target word, and these are your context words. The next iteration, this can be your target word, and these are your context words, and like that. You slide your window, you get many input examples. You log all those input examples, and that becomes the training instances for the algorithm. And this is typically the architecture that is used for skip-gram model. So, yeah. Okay, so you have one matrix here W, another matrix here W prime. These two are the parameters of the algorithm which are learned, and this explains the learning process. Again, let me skip this one because we don't have much time to explain this. So essentially, finally, it represents some score for all the words. So given these input, whether the probabilities of the other words for being a context word. Now these scores will be converted to probability by using some function. So one such function is softmax function, and this is that's the predicted probability. Now once we have the data, because if you remember, we had the training instances, right? We know the actual probabilities. We know the actually which words were there in as those words which we are trying to predict. And if that probability is there as the ground truth probability, we can compare these two vectors and compute the loss. And this loss can then be fed back in the architecture so that these parameters, that is this matrix and this matrix, they can be updated. Now here, there are quite a few things that people observed. This word-to-vec captures analogies very nicely. For example, if they look at the vector for man and the vector for woman, this translation vector, if they find out, what they saw is that this is very much similar to the translation vector that they get for aunt and uncle. Similar translation vector, if you apply on king, you get queen. So these are called word analogies. Similar things were observed for king to kings and queen to queens and so on. Some other analogies were like, from if you have the word China and the Beijing, and this translation, if you look at, this translation was very much similar to the translation that you need to reach Moscow from Russia in this vector space. Again, very similar translation vectors were needed to go to Madrid from Spain. So it captures the word analogies well, but it had some issues also. There were lots of societal bias that were observed from the embeddings. For example, there were many jobs, high-profile jobs, which were mostly assigned to male according to the vector space, and there were some other jobs which are generally considered as thankless jobs or considered as simple jobs. Those were getting attached to female genders. So this kind of stereotyping were being observed in the data as well. So there are many studies like that. Yeah. So this is about the gender stereotyping that was observed from the word-to-vec outputs, where the input were document collections from real world. Okay. Then people said whether there is a bias in the algorithm or bias in the data. Then the researchers, they argued that this was learned in an unsupervised way by looking at the documents which were fed to it. So if we are seeing any societal bias or gender bias in the final vectors, That is because the documents themselves contain that bias somehow, and this algorithm made it surface up. So that kind of reflects, if we assume that all the real things get replicated or get represented in the documents, that means our real life, in reality also, the things are like that only. So that is one thing that people highlighted, and it become a huge thing to consider now when people are talking about fairness and all. Then we did something where we said that, okay, instead of only passing the documents and making the algorithms learn from that, there are lots of other things that we can do on the sentences, right? For example, we are looking only at the small sliding window of size, say 5 or 7 or 9. Now there can be many related words in a sentence which are beyond that 5, 7 or 9 window size. Now shouldn't we be able to dictate to the algorithm that, okay, although these words are far apart, but they are related? And what if we can pass on these judgments to the algorithm? Is it able to learn better? So that we call at multi-context representation learning. So in NLP, there is something called a dependency parsing. So we have a dependency for each sentence. We can get the dependency tree, and long-range dependencies. There exist many long-range dependencies in real sentences. So those signals also we passed. Even from WordNet also we can get a lot of semantic information that also we passed. And by adding all these things in a framework to learn the representations, what we saw is that we can actually do much better from word to vec. So these were our algorithms for multi-context representation learning, and they were better than algorithms which do not look at other contexts, and many other algorithms which are also looking at the different other contexts. So this was one thing. And then another thing that people said is that, okay, suppose you have a document D which has words W1, W2, W3. So what you can do is you can get word to vec representation of W1, W2, and W3, and you can take the average of that then. So that gives you the document representation. Now the question became, what if W3 is a misspelling? Or misspelling which was not observed in the training data will not have any vector. So what do we have in this place? Now people said that, okay, you can ignore this. So essentially the representation of this will be average of W1 and W2, or you can replace it by a random vector, okay, and then take the average. But again, these appear suboptimal or some quick fixes, right? Not something which comes from some principle in a principled way. So then what this was a embedding scheme which came from Facebook. It is named as fast text. What it said is that for each word you get the character engrams. Okay, so for example, if you have the word where, you append a begin symbol and an end symbol, and then you look at 3 consecutive characters, right? Open WH, WHE, and like that, and this. And the final representation of the vector, okay, will be the sum of representations of this, and this. Sorry, not sum, average. So instead of learning only the representations of these words, also try to learn the representations of these small character engrams. So in this way, if you do it, even if you are observing misspellings or rare words, you can actually get their representations. So this was shown to be very powerful in many applications, and these were called subword vectors. So far the algorithms that we have seen, we saw that from this kind of one hot encoding, we got word embeddings like this, right? Where similar words can get grouped together in high dimensional vector space. But now people said even this could be inefficient because there can be many situations where the meanings of the words are context dependent. For example, if we say that banks lower home loan interest rates, then migratory birds on the river bank and do not bank on strangers, the same word bank or the same appearance bank has different meanings. So is it sufficient to have only one representation for bank, or depending on the sense and depending on the context, bank should have many different representations? Similarly, you can say CEO set the target, Nadal wins the first set, and let R be the set of numbers. Same word, many meanings. So right now, what people are doing is they are getting the representations dependent on the context. Okay, so 3 different sentences which have the word bank. So the sentences will be passed through contextualized word embedding algorithms, and if it will give a different representation to these 3 occurrences of bank depending on the contexts in which they appeared. And this is now being considered as the most powerful representation. So one of those representation schemes is called BERT, and it is based on transformer architecture, and this is actually the transformer architecture. So many of you may have seen the those transformers, right? They look very ugly from outside, and a lot of very serious and nasty things go on inside. This transformer is very similar to that. It looks very ugly, and inside there are a lot of different things, very powerful things which go on, but the outputs are excellent. So again, explaining the transformer architecture is beyond the scope of this talk. So what you can try to remember is that transformer architecture has 2 parts. One part is encoder and another part is decoder, which we can show like this: encoder and decoder. So this encoder has some input which actually comes from the words or the input sentences, and it produces some output which here goes to the decoder. Now you can actually stack one encoder on top of another encoder. So it's kind of this goes to another block of encoder, right? So this is what is shown in this diagram. So you can have a stack of encoders, and finally a stack of encoders, there can be a stack of decoders also. So BERT is one word representation scheme that actually uses the encoder side of transformer architecture and stacks together many encoder blocks like this. So you can consider that this is the BERT algorithm, which is a learning algorithm, which when fed as a collection of documents, it produces output, which is nothing but for each word, the vectors. Okay, so what is the learning that happens inside? So learning that happens inside is actually modeled as task. The first task could be, so you take a sentence, okay, and you mask some of the words from that sentence. Erase some of the words. And let us see whether the algorithm can predict those words in the output or not. Okay, so if it makes some mispredictions, it will compute a loss value, and that loss value is passed through the BERT architecture. It will adjust the parameters, and it will go on in iterations so that the parameters are learned best. There is another task where given 2 sentences A and B, predict whether A and B are consecutive sentences or not. Okay, so there the output could be yes or no. And one can actually mix these 2 tasks also, which as shown in this thing. Okay, so let me finish in the next 3 minutes. Yeah, so this mask is actually the masked word, and this separator indicates the separation between 2 sentences. So given sentence A and sentence B, predict whether they are next or not. So based on that, this architecture can be trained. Now this architecture, it will give a representation for each word, right? And this word is a generic representation, not task specific. Now as you know, for different, if you ask any sports person, right, about its fitness regime and so on, the person will definitely going to say is that, okay, I go to gym. Okay, so again, that gym is a very regular kind of thing if you think, but different sports require different kinds of skills. Now the person who is a tennis player, the kind of gym exercises that he does can be different from the person exercises that a swimmer follows. Okay, that will be different from the gym exercises that a basketball player follows. So when we say gym, it's actually the generic thing, but depending on the final goal, there inside the gym also there can be different other kinds of exercises that these people do. So this generic thing is actually called pre-training, and the task specific thing is actually called fine-tuning. So the representations which are learned by birds are actually coming through pre-training, but that needs to be adapted through some fine-tuning steps so that it can do well on the tasks which are of the final application, which are needed by the final applications like clustering, classification, and so on. So it has been shown that after pre-training, whatever we get from these architectures like BERT, so they can be adapted or fine-tuned to serve the purposes of many different tasks, which essentially shows how good or how nice these BERT outputs are. Okay, so once you have the representations learned by BERT, actually you can feed them to many different tasks. Like suppose you want to identify the hostile or bad posts in social media. You can do that. You take the BERT representation of the document and pass it to a classifier. You want to cluster the documents. Take the BERT representation of the documents and then you do k-means clustering. You want headline generation. You take the news article, you get the BERT representation of the document and pass it to a decoder in a sequence generator model, sequence to sequence model. It will give you the headline. Then finding similar prior legal cases. Again, take the BERT representation of the case description and earlier descriptions. You find semantic similarity between these BERT vector and other cases BERT vectors. So that can give you from that you can actually compute the similar documents. So one single representation scheme that can be adapted, that can be used in various different tasks. Okay, now this is not the end. There can be many different ways of getting the representations of the words and the documents. There can be better pre-training tasks. People are looking at different architectures instead of the transformer or even inside the transformer. People are curious about what can we do for languages other than English. What about Hindi, Bengali, Tamil, Telugu, Punjabi, all these languages? Can we have word representations for that? Now, can we align embeddings of the terms across languages? Lose and har and defeat. Can we have the representations of these similar, although they may come from different languages? Then there are talks about application-specific fine-tuning, single fine-tuning for multiple tasks, and many newer applications which can make use of these good quality representations or embeddings. So with that, let me finish my my side of the discussion. If there are any questions, you may please go ahead and ask.